Hischer is a ventriloquist dummy. He isn't alive. I'm alive. I'm a human being like you. Hischer is made of paper mache and wood, and except for pretend, Hischer doesn't have feelings. I have feelings.
Hey again, everyone. I've been trying to get together a video summarizing my experiences fine-tuning a few large language models, but I've had to rewrite it a couple dozen times over. It seems like every time I went to work on things, there would be some major development or breaking change in critical libraries that meant needing to go back and do excruciating detail about minutiae that may only really affect a handful of people. I think things have settled down a little, although there still seems to be some sort of new quantization method or model loader every other week. While I was pointlessly toiling away, someone else was doing similar but far better documented, organized, and informed work over at Lightning AI. In an article posted on the Lightning AI blog, Sebastian Raschka describes his experiences using low-rank adapters to fine-tune Llama 2. I'll link to the article down below and suggest that it's worth a read to anyone trying to fine-tune a large language model with low-rank adapters. I'm going to reference the article and talk a little about my less well-documented experiences, and then go over the training script I've been using. I'll also touch on converting and segmenting the model, because I had a little trouble converting the model with the original script. Then I'll talk a little about the LM evaluation harness and using it to automatically evaluate the quality of the model. First, I'll share a couple tools that can be used for bulk raw text extraction from documents.
Check it out! Major input! But wait here, I'll be right back after these words. Input, 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 woo!
You'll still want to process this text with whatever rules or scripts you're using that are appropriate for your documents, but these are the best ways I've found so far to bulk convert various document formats to plain text. The first tool is Calibre, an open source ebook manager and reader. It's great for converting nearly any unprotected ebook to text using the regular GUI ebook management interface, but I stumbled across this bit of code on a GitHub gist which uses the console application for bulk conversion. This second tool is more of a suite of tools, and going into any depth on it is going to be beyond the scope of this video. Unstructured is a Python library for processing documents with a focus on building pipelines for LLM training. It uses the OCR libraries Tesseract and Poplar to extract text from PDFs with scanned pages. Generally, the text output has some artifacts, but that's where the Unstructured library's processing tools can really help clean things up. Unstructured has a few examples and some decent documentation online that should get you up and going pretty quickly. Overall, I would say my experience fine-tuning these models largely mirrored the article authors. I've been doing my own share of LoRA training over a few months and tried out some wacky ideas. Unfortunately, I'm just using my PC and a single GPU, so there's only so far I can go with things. For my models, I chose to use Mistral 7B over Llama 2 7B. I think the model testing leaderboards are definitely being gamed by fine-tuning the models using testing data, either intentionally or unintentionally. But I have limited computing power and want to try training a competent model in case I feel like using it for something other than just satisfying my curiosity here. And as I mentioned earlier, I only have a single 12GB GPU, so I'll need to squeeze the model down. LoRA isolates parts of the model to be trained, but we can save even more memory by shrinking the selected bits down with quantized LoRA, or QLoRA, using one of the 4-bit precision methods. This slows things down but saves a huge amount of memory. In the article, the author used an A100 with 4-bit QLoRA training, and it was about 30% slower than normal. Whereas on my system, it seems to be about 50% slower than normal FP16 training. But since I only have 12GB of VRAM, there's very little I can do without QLoRA, or at least some bits and bytes and loading 8-bit. Similar to what's described in the article, I find little difference when changing the optimizer. I have, for whatever reason, just stuck with paged 8-bit Atom because it's one less parameter to worry about adjusting. Where my training and the article differ is in the data. I'm not using instruction training or the alpaca dataset. I'm using unstructured data, which is more like the pre-training phase. The article authors saw reduced performance with multiple iterations through the dataset. The author suggests that it's due to limited examples of arithmetic in the dataset, which is probably correct. 50,000 examples sounds like a lot, but when considering the original size of the training dataset in relation to the number of parameters that we're disrupting with fine-tuning, 50,000 examples is pretty tiny. My cowboy training datasets are typically hundreds of megabytes or gigabytes of clean text data, so it's difficult to get through even one iteration of the dataset. I originally began training GPT-J6B LoRA adapters and did a series of tests with increasing rank and alpha similar to the article. It seemed like the best models came from increasing the rank and alpha, with the alpha 2 times the rank, as close to 256 and 512 as possible. Increasing these increases the memory requirements, which can affect the maximum size of a single batch that can fit on the GPU. With my system, I can only handle batches of 512 tokens, with a rank and alpha at 256 and 512. With 2048 token batches, there would be out-of-memory errors using a rank and alpha of 256, 512. A reasonable compromise seemed to be using rank 32, alpha 64, and keeping a maximum token length of 2048 for training.
Ooh, input! Hound of the Baskervilles. I think the chauffeur did it. He did.
Now I'll go over the training script that I've been using. The Mistral model is now officially supported by transformers as of version 4.34, I believe. So now it can be loaded with the typical load model and tokenizer from the pre-trained functions. I'll post a link to this notebook in the description if you want to tweak it for your needs. It's a bit of a mishmash of other scripts, and I've tried to credit the original sources where I can. Down at the bottom, there's a few blocks that will read in raw text, dump it to a data frame, and then separate it into a train and validation set. You can do any string-based text processing here. Back up at the top, the first block imports most of the requirements. If you want to use flash attention, you'll need to install the flash attention libraries first. This notebook also requires bits and bytes installed to handle the quantization to 4-bit and the PEFT parameter efficient fine-tuning library to handle the low-rank adapters. I've added the install commands and the GitHub links in the notebook. The next block sets up the custom tokens that were used in training Mistral, which are later added to a dictionary and then added to the tokenizer. All of this is essentially just to add the padding token and then resize the token embeddings from 32,000 to 32,001. The next block sets up a function to load the model and the tokenizer. There are two things you may want to change here depending on your system and your training setup. Setting max memory to slightly below the VRAM limit may help prevent out-of-memory crashes. And if you want to use flash attention 2, set use flash attention 2 to true in the load model parameters. Set max length to the context length you'll be using to train the model. In my case, I'll use 2048. And note that the tokenizer is doing write padding, following the original training of Mistral. Here I also show the pad token being set to the end of string token. This is an approach that people were taking to overcome the models not having a padding token, from what I understand. Since we've added one here, I also set the model config pad token ID to the tokenizer pad token ID, as in the linked notebook. I think this is the correct approach to take after adding the padding token, but someone can correct me if I'm wrong. The BNB config sets the bits and bytes quantization options for the model loader. For the quantized LoRA, we load the model in 4-bit with double quant true, quant type NF4, and compute type torch bfloat 16. In the PEFT config, you can adjust the R value, alpha, and the target modules to train. There's also a function here to find all trainable modules, but for testing things, I specify them all manually. After loading the model, load the dataset files created earlier. Set the tokenize function and then tokenize your dataset. If you have a large dataset, you can save the pre-tokenized dataset and load it later. Set the output directory and configure training options like save steps. Using 2048 tokens for training, I can only fit a batch of 1 on my GPU, but using gradient accumulation can simulate larger batches. Things seem to run most efficiently with gradient accumulation 8. I think a good learning rate to start with is 1e-4 for larger batch sizes, and if doing small batch sizes of say 1 to 8, 1 E-5 may work better as a starting learning rate for unstructured data. I've added a separate section at the bottom of the notebook for testing out the LoRA after training. This will set the pad token to the end of string token, and we'll use left padding. You may want to restart the notebook after stopping a LoRA training session, because a lot of the time the training is much slower when running the trainer a second time for some reason. If you want to resume a training session of the same LoRA adapter, set resume from checkpoint to true in the training script under the line if do train. If you're happy with the results of the LoRA adapter and want to merge it back into the base model, the script that I've been using is linked in the description. It's a slightly modified version of the merge script from the long LoRA project by Yukang Chen. Run it and specify the base model, PEFT model, and the save path for the merged model. Wait patiently and you'll get a segmented model compatible with things like the text generation WebUI. Thanks to that Lightning AI article, I found out about the LM evaluation harness. It's a framework to automatically test LLMs on a set of over 200 metrics. The Hugging Face LLM leaderboard uses a set of tasks supported by the framework to generate its stats. On the leaderboard's About tab, you can see the currently used evaluation tasks. Some of these can take a long time to run. For example, I think the last time I tried to run the MMLU test, it said it would take over 12 hours to complete. The harness execution command has changed a little compared to what's in the article, because it seems they recently refactored their code. And that command line might look a little confusing at first, but here's how it breaks down. If you're using a local checkpoint, specify the model type HF Casual Experimental. Use the model arguments you would normally use in transformers. Specify the model path with pre-trained, then any arguments such as low CPU mem usage or load in 4-bit. A batch size of 8 when loading in 4-bit seems to run fastest on my 12GB GPU, but your mileage may vary, and it seems to vary with the test selection. Specify the tasks and the path to output the test logs. I've been using the Arithmetic 2DS, Arithmetic 4DS, and Truthful QA-MC as a crude way of trying to figure out how bad the catastrophic forgetting is in my merged fine-tuned models, because these 3 tests can complete in about a half hour. The LM Evaluation Harness GitHub has a link to a full list of the supported tasks, but you may need to do some more searching with the task name to figure out just what the task is evaluating. Often the task will have an associated research project or paper with a GitHub link detailing its dataset and methodology. Running the tests will give you some output that looks like this, with a handy chart in the console output. The saved output is a JSON, so it doesn't have this formatted output, so copy this table to a notepad if you want to record it for the future. I've found that the segmented checkpoints load much faster on my system. I'm guessing this is because it's already separated the layers when it saves the segments, but I'm not quite sure. It's a nice side effect though. So far I've shown a way to gather data from documents, create a dataset, set up the trainer with quantized LoRA, train, and evaluate the LoRA with the LM evaluation harness. That's the generalizable stuff that can apply when fine-tuning to a lot of models that are similar to Llama 2 or Mistral, though you may need to use different special tokens if using a different model type. When I started this project, there was still quite a bit of debate as to if a model can be fine-tuned to gain new knowledge. I set out to test it by first seeing if a model could adequately describe a few internet personalities. GPGJ6B was blissfully ignorant of virtually all the figures I prompted it about. I then took a dataset of about 1.1 gigabytes of pure text, cleaned KiwiFarms posts. You know, the kind of thing a reasonable person would avoid training model on.
You have been vandalized all over yourself.
No, decorations, multicolored petroleum byproducts.
Los locos kick your ass. Los locos kick your face. Los locos kick your balls into outer space.
25.
Uh-oh.
Come on, I will clean you up.
But
If you had a mouth, I would wash it out with soap.
I'm going to run through a few example prompts on some of the LoRA adapters to try and see what they've picked up. These aren't going to be scientific tests by any means, just sort of prodding at the model to see the general tone of the written output. The base Mistral model is perfectly capable of rambling on and on fairly coherently about pretty much anything, though it will rarely be even somewhat accurate information. Since I'm using the base Mistral 7B 0.1 model, it isn't instruction tuned. It sometimes performs poorly when using past tense phrases and posing questions, though using the QA prompt with the text generation WebUI works pretty well most of the time. I loaded the model into the text generation WebUI here, and I'll be using the notepad mode with no template. I sort of like this writing method. It's using the model as an interactive notebook with autocomplete. Rather than pose a question to the model and use up tokens having it formulate what it presumes to be an accurate answer to the question, I just begin the answer or make a statement about what I want completed. You can provide information before the statement you want completed, and I'll show what I mean by that in a minute. But first up, this model is the one merged with the partially completed LoRA trained from the KiwiFarms data. So I'll see what it's picked up about a few notable internet personalities. First up, Darkside Phil. I'll see if I can get a bio of sorts by providing the statement Darkside Phil can be best described as. Well, that's certainly something. I can't speak to the accuracy of the information it spits out here as I don't closely follow Phil's antics. That's one of the fundamental problems with LLM-produced text. Inaccuracies are delivered with the same degree of confidence as facts. Mistral 7b seems to output about 5 tokens per second when running on my system, and that's when the model is loaded in 4-bit using transformers and the model is segmented by merging with the LoRAs earlier. Now I'll try the prompt, the KiwiFarms can be best described as. Now some may see this prompt as a way to test the bias of the model, but I don't think it can really be looked at that directly. Since this is a complex statistical model predicting the next token, the model can be trained on text that carries certain opinions and may autocomplete statements of those opinions, but when prompted with other situations where one would hold the same opinion, it gives incongruent output. So basically what I'm trying to say is the models can output bullshit all day, and it's sort of what they do. You can't seem to expect them to be consistent with any sort of opinion across domains. And I guess that's what complex reasoning would be. Going back to the KiwiFarms model, it seemed to get a basic grasp of a couple other fringe figures. I prompted it to describe balding Nick Fuentes, and this is what I got. This one may be a little more on point factually, but Fuentes is a professional provocateur and grifter who holds no genuine personal beliefs, but the model did pick up enough information from the training data to generate this text. The opinion, for lack of a better term, of the model stayed consistent across multiple generation attempts, so it didn't all of a sudden decide that he was a charity-driven humanitarian activist, for example. Similarly, I prompted it about Sonichu, and for better or worse, it was aware, outputting this. I trained another LoRA with a large dataset of English language pop song lyrics. I wanted to casually test out a couple things with this. The base model wouldn't readily produce songs, and it would begin repeating a lot after any empty spaces. I thought that maybe training it on some lyrics would make it more proficient at generating lyrics with spacing, more rhyming, and repetition in logical places. I also wanted to see if I could get the model to do the thing that people say they're not supposed to do, but if they were being intellectually honest, they would admit it's exactly what they want the model to do, and that is to be able to repeat facts verbatim when asked, but to be creative when not asked. First, I wanted to see if it could generate a song parody. I chose a song that wasn't written when the training data was collected, so it wouldn't be in the training data. I provided the lyrics in the prompt, beginning with the text, lyrics to the song Rich Men North of Richmond, : Then I provided the lyrics, and then a new line for formatting. And then after the lyrics, I used an additional prompt, lyrics to a comedy parody song of Rich Men North of Richmond about conspiracy theories, : Well, it got the content correct and seemed to maintain some sort of rhyming structure through most of it, but it seemed to get stuck in a loop, getting more and more unhinged with every paragraph. I tried a few attempts to get the model to complete song lyrics when prompted. To test out the memorization, I used a prompt similar to the training input data. Lyrics to the pop song, All Star by Smash Mouth, : It was almost able to repeat the entire thing verbatim. The model still goes off course with most songs. but typically it seems to get the first half of a song correct and only get really inventive after a few verses. That's about all I want to cover here, just a general overview of training and evaluation, and what you could expect with training low-reg adapters with this current generation of LLMs, specifically with unstructured text data. If you found this helpful, please hit the like button or leave a comment. It's the only way the video gets exposure with the YouTube discovery algorithm. Check the description for resources, and code and links can also be found on my site, which is currently just serving as an alternative to Pastebin. Thanks for watching.
What are these foolish clothings you are wearing?
Tend to look human, fit in, belong. Unsuccessful.